Look up at the night sky, and you'll see stars twinkling like scattered diamonds. But beyond that serene view lies something far more dynamic, almost alive. Out there in the vast darkness, galaxies aren't just floating aimlessly, they're dancing. Picture two spiral galaxies, each with billions of stars, slowly twisting toward one another, their arms stretching like partners in a cosmic waltz. Gravity pulls them closer, distorting their shapes, sending streams of starlight swirling into space like ribbons caught in the wind. This isn't just a rare event, it's happening right now, all across the universe, in a spectacle so grand it defies imagination. Welcome to the dance of galaxies, where celestial bodies move with a rhythm older than time itself, and every collision, every near miss, tells a story about the universe's past and future. For centuries, humans could only guess at these galactic ballets. Telescopes showed us static pinwheels of light, but modern science has peeled back the veil. Now we can see galaxies not as frozen snapshots, but as dynamic actors in an endless cosmic drama. Advanced simulations, space telescopes, and cutting-edge physics reveal how these dances shape everything around us, from the birth of new stars to the invisible tug of dark matter, a mysterious force that holds the universe together like an unseen choreographer. What we've learned is both humbling and thrilling. Our Milky Way is part of this dance too, destined to merge with the Andromeda galaxy billions of years from now, rewriting the night sky forever. But how do scientists decode these movements? What secrets do these galactic interactions hold about the universe's origins, or its ultimate fate? In this video, we'll journey through the tools and techniques astronomers use to track these celestial performances, from redshift measurements that reveal galaxies speeding away from us to supercomputer models that recreate cosmic collisions down to the last detail. We'll explore how these dances expose the hidden architecture of the cosmos, from dark matter's gravitational grip to the way galaxies evolve over eons. By the end, you'll see the night sky differently, not as a static canvas, but as a stage where galaxies whirl, collide, and transform in a show that's been running for 13.8 billion years. So let's step into the observatory, peer through the lens of modern science, and uncover the breathtaking story written in the movements of the stars. To understand the grand dance of galaxies, we first have to look at the stage they're performing on, a vast, interconnected cosmic web stretching across the universe. Picture it like an enormous spider's silk, with threads of galaxies woven together by gravity, forming clusters, superclusters, and immense walls of matter. Our own Milky Way isn't floating alone. It's part of a small neighborhood called the Local Group, which includes Andromeda and dozens of smaller galaxies, all gently tugging at one another in a slow-motion ballet. But zoom out further, and you'll see even larger structures like the Laniakea supercluster, a sprawling family of galaxies spanning over 500 million light-years, all moving together in a shared cosmic river. What keeps these galaxies in motion? The answer lies in the invisible scaffolding of the universe's dark matter. Though we can't see it, its gravitational pull shapes everything. Think of it like the backstage crew of a theater production, unseen but essential, dictating where and how galaxies move. Without dark matter's influence, galaxies would drift apart, their delicate dances falling out of sync. Scientists map this hidden structure by observing how galaxies move, how light bends around them, and how they cluster together. It's like piecing together a puzzle where most of the pieces are invisible, yet their presence is undeniable. These immense structures don't just dictate motion, they also determine destiny. galaxies caught in the same gravitational flow will eventually meet, merge, or fling each other into new trajectories. Our own Milky Way and Andromeda are on a collision course, pulled together by the same forces that have shaped cosmic history. But this isn't chaos, it's a carefully orchestrated motion, guided by the universe's hidden architecture. Every galactic dance step, from a gentle gravitational tug to a full-blown merger, leaves clues about how the cosmos evolved and where it's headed next. Gravity is the silent maestro behind every celestial motion, the unseen hand guiding galaxies in their endless dance across the cosmos. Imagine the universe as a vast ballroom where galaxies glide and spin not by chance, but by the precise pull of this fundamental force. Einstein's theory of general relativity revealed that gravity isn't just a tug between objects, it's the bending of space-time itself, like a heavy ball resting on a stretched sheet, warping the fabric around it. When galaxies pass near one another, their immense mass creates these cosmic dimples in space-time, drawing them together in a slow, inevitable embrace. Some interactions are graceful, like two partners circling each other at a distance, their mutual attraction shaping delicate tidal tails of stars and gas. Others are far more dramatic, like the head-on collisions that send shockwaves through entire galaxies, triggering bursts of star formation or flinging stars into intergalactic space. Take the Antennae galaxies, for example, a pair of spirals caught in a violent merger, their arms stretched into long, luminous streamers resembling insect antennae. These collisions aren't destructive chaos, they're transformative, recycling gas and dust into new generations of stars and planets. Yet gravity's influence extends far beyond individual galaxies. It weaves the universe's largest structures, from galaxy clusters to the filamentary cosmic web, acting like an invisible scaffold that dictates where and how matter accumulates. Without gravity, galaxies would never have formed in the first place. Primordial gas would have drifted aimlessly, never condensing into the brilliant islands of light we see today. Even now, gravity continues to sculpt the universe, pulling superclusters toward one another in a slow-motion rearrangement that will take billions of years to unfold. What's truly remarkable is how astronomers decode these movements. By measuring the subtle shifts in starlight, tracking the orbits of stars within galaxies, and simulating gravitational interactions with supercomputers, they've pieced together the rules of this cosmic ballet. Gravity doesn't just explain why galaxies move, it reveals their histories. The way a galaxy spins, the paths of its satellite galaxies, even the distribution of dark matter within it, all are fingerprints of gravity's relentless work. And as we peer deeper into the universe, we're discovering that this force doesn't just connect galaxies, it connects us to the very fabric of reality, a thread tying everything from the smallest planet to the largest supercluster into one grand, intricate dance. Dark matter is the universe's best-kept secret, an invisible force holding galaxies together, yet leaving no trace of itself except the gravitational pull it exerts. Imagine trying to hear a symphony where most of the instruments are silent, their presence revealed only by the way the music swells and bends. That's the challenge astronomers face when studying dark matter. It doesn't emit, reflect, or absorb light, making it completely undetectable by traditional telescopes. Yet its influence is everywhere. Stars on the outer edges of spiral galaxies whirl around their centers at speeds that defy the laws of physics unless there's an unseen mass, a hidden anchor, keeping them from flying off into the void. That anchor is dark matter, an enigmatic substance making up roughly 85% of the universe's total mass. Without it, galaxies as we know them couldn't exist. Take the Milky Way's graceful spiral arms. Those swirling lanes of stars and gas should unravel over time, their outer stars drifting away like leaves in the wind. But they don't, because dark matter's gravitational grip holds them in place. It's not just about structure, though. Dark matter also dictates how galaxies move on the grandest scales. When astronomers observe clusters of galaxies, they find they're moving too fast for the visible matter alone to keep them bound. There must be something more, an invisible scaffold woven through the cosmos, keeping everything tethered. So how do we map something we can't see? Scientists use ingenious methods like watching how light bends around massive galaxy clusters, a phenomenon called gravitational lensing. The more a cluster warps the light of distant galaxies behind it, the more dark matter it must contain. Supercomputer simulations take it further, recreating the universe's evolution with and without dark matter. The results are striking. Simulations without dark matter show a universe where galaxies never form properly, where matter drifts aimlessly. Add dark matter, and suddenly the simulations mirror reality, with galaxies clustering just as we observe. The dance of galaxies isn't just about the stars we see, it's about the unseen partner guiding every step. Dark matter's gravitational choreography shapes cosmic history, from the first galaxies to the colossal structures we see today. And while we still don't know what dark matter truly is, whether it's made of undiscovered particles or something even more exotic, its fingerprints are all over the universe, a silent maestro conducting the grandest performance of all. Galactic collisions are the universe's most spectacular performances, where the slow, graceful dance of galaxies erupts into a breathtaking cosmic tango. Picture two massive spirals, each containing hundreds of billions of stars, hurtling toward one another at staggering speeds. At first, their movements seem almost gentle gravities pull, stretching their arms into long, luminous ribbons of gas and dust. But as they draw closer, the interaction turns chaotic. Stars don't actually crash into each other. Space is too vast for that, but the gravitational turmoil flings them into new orbits, warping the galaxies beyond recognition. Gas clouds collide, compressing under immense pressure and igniting fireworks of newborn stars. What was once two distinct galaxies becomes a single, brilliant mess, a celestial masterpiece in the making. Take the Antennae galaxies, for example. Named for their long, antenna-like tails of ejected material, these two spirals have been locked in a gravitational embrace for hundreds of millions of years. Their collision has sparked a frenzy of star formation, with clusters of young, blue stars blazing like diamonds scattered across the wreckage. Yet amid the chaos, there's order. Over time, the Antennae galaxies will settle into a single, larger galaxy, likely an elliptical, its stars orbiting in random directions like a swarm of bees, a far cry from the neat spirals they once were. This isn't just destruction, it's transformation. Collisions recycle the raw materials of the universe, turning old stars into new ones and reshaping galaxies into entirely different forms. Our own Milky Way is no stranger to these cosmic mergers. It's already cannibalized smaller galaxies, like the Gaia Enceladus dwarf galaxy, whose stars still orbit within ours like ghostly remnants of a long-ago feast. But the biggest event is yet to come. In about 4 billion years, the Milky Way and Andromeda, our closest galactic neighbor, will begin their fateful collision. Simulations show the two spirals first passing through each other, their gravity twisting their shapes into wild, unrecognizable forms. Stars will be flung into new paths, though our solar system will likely survive unscathed, carried along like a leaf in a river. Over billions of years, the galaxies will merge into a single, colossal elliptical galaxy, nicknamed Milkomda. The night sky, once dotted with familiar constellations, will be utterly transformed, filled with strange new patterns of light. These collisions aren't just spectacular to watch, they're vital to understanding how galaxies grow and change. By studying mergers across the universe, astronomers have pieced together a startling truth. Most large galaxies, including ours, owe their size and shape to past collisions. Every massive elliptical galaxy we see is likely the product of multiple mergers, each one adding stars, gas, and dark matter to the mix. Even the universe's largest structures, like galaxy clusters, are shaped by these interactions, their members constantly tugging and tearing at one another in a slow-motion reshuffling of cosmic real estate. What's truly remarkable is how much these events reveal about the invisible forces at work. The way galaxies collide, how their stars move, where their gas collects, hints at the distribution of dark matter, the universe's hidden scaffolding. Collisions can even strip galaxies of their gas, leaving them red and dead, unable to form new stars. By witnessing these cosmic crashes, we're not just watching galaxies evolve, we're glimpsing the rules that govern the entire universe, written in the language of gravity, motion, and light. Every collision is a chapter in a story billions of years in the making, and we're just beginning to read it. The Milky Way isn't just some static backdrop in the night sky. It's a dynamic, ever-moving participant in the grand cosmic dance. Right now, it's gliding through space at over 600,000 miles per hour, pulled by the gravitational tides of nearby galaxies and the unseen influence of dark matter. But this isn't a solo journey. Our galaxy has a long history of interactions, some violent, some subtle, each leaving its mark. Take the Gaia Enceladus dwarf galaxy, for instance. Billions of years ago, this smaller neighbor collided with the Milky Way, and its stars were torn apart, scattered into streams that still orbit us today like celestial breadcrumbs. These stellar streams are more than just relics, they're clues, helping astronomers reconstruct the Milky Way's past and predict its future. Then there's the Great Attractor, one of the universe's most puzzling mysteries. Located roughly 250 million light-years away, this invisible gravitational behemoth is pulling the Milky Way, along with thousands of other galaxies toward it at incredible speeds. For decades, its exact nature eluded scientists, hidden behind the dense plane of our own galaxy. But recent observations suggest it's not a single object but a colossal concentration of mass, likely a supercluster of galaxies wrapped in dark matter, bending space-time like a cosmic whirlpool. The Milky Way isn't just moving aimlessly, it's being drawn into this gravitational current, part of a vast, slow-motion migration of galaxies across the universe. But the most dramatic chapter in our galaxy's story is yet to come. In about 4 billion years, the Milky Way and Andromeda will begin their inevitable collision, a merger that will reshape both galaxies forever. Even now, Andromeda looms in our skies, inching closer at nearly 250,000 miles per hour. When they finally meet, the night sky as we know it will vanish, replaced by a dazzling, chaotic display of new stars and twisted spiral arms. Yet despite the colossal forces at play, individual stars are so far apart that our solar system will likely sail through unscathed, a tiny spectator to one of the universe's most breathtaking events. What's fascinating is how these movements reveal the hidden architecture of the cosmos. By tracking the Milky Way's motion, scientists have mapped the distribution of dark matter, uncovered lost galaxies absorbed long ago, and even glimpsed the large-scale flows that govern the universe's expansion. Every wobble, every shift in our galaxy's path tells a story about the forces shaping it, the neighbors influencing it, and the fate awaiting it. We're not just observers of the cosmic dance, we're part of it, carried along by gravity's unbreakable grip, spinning toward a future written in the motions of the stars. Andromeda isn't just another spiral galaxy in the night sky, it's a ticking clock, a cosmic inevitability racing toward us at nearly 250,000 miles per hour. Right now, it hangs there, a hazy smudge of light, but in 4 billion years, that faint glow will dominate the heavens, growing larger and brighter as it nears its fateful embrace with the Milky Way. When these two giants finally meet, their collision won't be a fiery crash of stars colliding. Space is far too vast for that, but a slow, gravitational waltz that reshapes both galaxies beyond recognition. Picture two immense spirals, each with hundreds of billions of stars, their arms twisting and stretching like taffy as gravity pulls them into a swirling, chaotic merger. Over billions of years, they'll coalesce into a single, colossal elliptical galaxy, a behemoth astronomers have nicknamed Milkomda. Simulations of this event reveal just how dramatic the transformation will be. As Andromeda and the Milky Way first sweep past each other, their gravitational pull will warp their shapes, flinging streams of stars and gas into long, luminous tails, cosmic debris marking the violence of the encounter. Stars will be tossed into new orbits, some hurled into intergalactic space, while others settle into chaotic paths around the newly merged core. Yet amid this upheaval, most stars will sail right past one another, untouched. Space is so empty that even in a head-on collision, stellar collisions are vanishingly rare. Our own solar system, it'll likely be carried along for the ride, orbiting farther from the galactic center but otherwise unharmed. What's truly fascinating is how this merger mirrors countless others that have shaped the universe. Look at any massive elliptical galaxy, and you're likely seeing the aftermath of a similar cosmic tango. These galaxies, with their smooth, football-like shapes and randomly orbiting stars, are the end products of violent mergers, their once orderly spirals scrambled by gravity's relentless pull. The Milky Way and Andromeda are destined to follow the same path, their identities erased as they become something entirely new. But this merger isn't just about destruction, it's about rebirth. The collision will compress vast clouds of gas, triggering bursts of star formation that light up the newborn galaxy like fireworks. New solar systems will form from the ashes of the old, and for a time, Milkomda's skies will blaze with young, blue stars. Eventually, though, the gas will run out and star formation will slow, leaving behind a quieter, redder galaxy, its stellar population aging together. This impending collision is more than just a distant spectacle. It's a reminder that galaxies aren't static islands in space. They're dynamic, ever-changing entities, growing and evolving through mergers and interactions. By studying Andromeda's approach, astronomers aren't just predicting the Milky Way's fate. They're piecing together the life cycle of galaxies across the universe. Every measurement of Andromeda's motion, every simulation of its collision, brings us closer to understanding how galaxies form, grow, and eventually fade, a story written in the slow, inevitable dance of the cosmos. Galaxies aren't just born massive, they grow by devouring their neighbors. This process, known as galactic cannibalism, is one of the universe's most dramatic ways of reshaping cosmic landscapes. Picture a vast, swirling spiral like the Milky Way, its gravity reaching out like invisible fingers, pulling in smaller, vulnerable galaxies. Over billions of years, these encounters leave behind scars, ghostly trails of stars called stellar streams, stretched across the sky like cosmic breadcrumbs. One of the most famous examples is the Sagittarius dwarf galaxy, a tiny neighbor slowly being torn apart by the Milky Way's gravity. Its stars are scattered in long, looping ribbons around our galaxy, a silent testament to the violence unfolding over eons. But it's not just stars that tell this story. globular clusters, dense, ancient balls of stars orbiting the Milky Way, are like fossils of these galactic meals. Some of these clusters don't match the chemistry or motion of the Milky Way's native stars, revealing they were stolen from other galaxies during past mergers. Take Omega Centauri, the brightest globular cluster in our sky. Unlike its peers, it spins faster, contains stars of varying ages, and even has a hint of a black hole at its core. Astronomers now suspect it's not a true globular cluster at all. It's the leftover heart of a dwarf galaxy the Milky Way consumed long ago. These mergers aren't just historical footnotes, they're key to understanding how galaxies evolve. When a small galaxy falls into a larger one, its gas and dust can trigger waves of new star formation, while its dark matter subtly reshapes the winner's gravitational field. The Milky Way, for instance, has likely absorbed dozens of smaller galaxies over its lifetime, each one adding stars, gas, and dark matter to its structure. Even now, it's in the process of digesting the Cannibalism's major dwarf galaxy, whose stars are peppered throughout our galaxy's outer reaches. What's astonishing is how delicate this process can be. When a dwarf galaxy is pulled into a larger one, its stars aren't instantly assimilated. Instead, gravity stretches them into vast, looping streams that can persist for billions of years. The Gaia spacecraft, mapping the positions and motions of over 1 billion stars, has uncovered dozens of these faint trails, each one a remnant of a past merger. By tracing their paths backward, astronomers can reconstruct the Milky Way's violent history, like detectives piecing together a crime scene from scattered evidence. This isn't just about the past, though. Galactic cannibalism continues today, shaping the future of our cosmic neighborhood. The Large and Small Magellanic Clouds, two small galaxies orbiting the Milky Way, are destined to meet the same fate. Simulations show they'll eventually be torn apart, their stars joining the Milky Way's halo. Even Andromeda, our future collision partner, has its own history of galactic meals. Its outskirts are littered with streams from devoured dwarfs. The lesson here is clear: no galaxy is an island. From the tiniest dwarfs to the mightiest spirals, growth comes through encounters, mergers, and yes, cannibalism. Every stellar stream, every mismatched globular cluster, tells a story of cosmic survival, where the biggest galaxies grow by consuming the smallest. And as we map these remnants, we're not just uncovering the Milky Way's past, we're glimpsing the universal rules that govern how all galaxies evolve, one merger at a time. Tidal tails are the universe's way of leaving fingerprints on the cosmos, long, shimmering trails of stars and gas stretched into space by the gravitational tug of war between colliding galaxies. These luminous ribbons, sometimes spanning hundreds of thousands of light years, are more than just cosmic debris. They're forensic evidence telling the story of how galaxies interact, merge, and transform over billions of years. Take the famous Antennae galaxies, their namesake tails arcing outward like the delicate feelers of an insect. These structures didn't form by chance. They're the direct result of two spiral galaxies brushing past each other, their gravity pulling stars and gas into dazzling streamers that glow against the darkness of space. But tidal tails aren't just beautiful, they're packed with information. By studying their shape, length, and even the speed of stars within them, astronomers can reconstruct the precise dance steps galaxies took during their encounter. The longer and more pronounced the tail, the stronger the gravitational forces at play. The distribution of stars within these streams reveals whether the interaction was a glancing blow or a near head-on collision. Even the color of the light they emit tells a story. Blue hues indicate regions of frantic star formation, where gas compressed during the encounter ignites new stellar births, while redder tones betray older populations of stars flung outward like scattered embers. Some of the most striking examples come from galaxies like NGC 4038 and NGC 4039, nicknamed the Ringtail Galaxy for the spectacular loop of stars stretching between them. Here, the tidal tail isn't just a straight line, it's a graceful arc. A frozen snapshot of the moment gravity bent the paths of countless stars into a celestial ribbon. Then there's the Tadpole Galaxy, whose tail stretches nearly 280,000 light-years, over twice the length of the Milky Way's disk. Embedded within it are clusters of young, blue stars, proof that even in the chaos of a galactic encounter, new worlds can emerge. These structures also expose the hidden hand of dark matter, since tidal tails follow the gravitational contours of their parent galaxies. Their shapes hint at where and how dark matter is distributed. If a tail curves unexpectedly or stars move at odd velocities, it suggests invisible mass is warping space-time in ways we can't see directly. In this way, tidal tails act like cosmic X-rays, revealing the skeleton of dark matter that holds galaxies together. What's truly remarkable is how long these tails persist. Unlike the violent collisions that spawn them, tidal tails can endure for billions of years, slowly fading as their stars disperse into intergalactic space. The Milky Way itself bears the scars of past encounters, faint stellar streams like the Sagittarius tail, remnants of a dwarf galaxy torn apart by our own. These ghostly trails are more than relics, they're active records of our galaxy's growth, proof that even the quietest corners of the universe are shaped by colossal gravitational dances. Every tidal tail is a chapter in a story much larger than itself, a story of attraction, disruption, and the endless transformation of the cosmos. Galaxies spin like cosmic carousels, their stars whirling around a central hub in a motion that should follow predictable rules, except it doesn't. In the 1970s, astronomer Vera Rubin made a discovery that shattered our understanding of galactic motion. She found that stars at the outer edges of spiral galaxies were moving far too fast, their speeds defying the laws of gravity as we knew them. According to Newtonian physics, the farther a star is from a galaxy's center, the slower it should orbit. Just like planets in our solar system, Pluto crawls compared to Mercury. But Rubin's observations showed something startling. No matter how far out you looked, stars raced along at nearly the same speed as those near the core. It was as if a ghostly hand was gripping the galaxy's outskirts, holding stars in place with an invisible force. This anomaly, captured in what astronomers call rotation curves, graphs plotting star speeds against their distance from the center, became one of the most compelling clues for dark matter's existence. Visible matter alone couldn't account for the gravitational pull needed to keep these stars from flying off into the void. Rubin's work revealed that galaxies are embedded in vast, invisible halos of something we still don't fully understand, halos that outweigh the stars and gas we can see by a factor of 5 to 1. Imagine a merry-go-round where most of the horses are invisible, yet their weight keeps the ride spinning smoothly. That's the paradox dark matter solves. Rotation curves aren't just historical footnotes, they're still vital tools for probing galactic secrets today. By measuring how stars and gas move within galaxies, astronomers can map the distribution of both visible and dark matter, revealing how these invisible halos are structured. Some galaxies have rotation curves that rise steeply at their cores, hinting at dense concentrations of dark matter, while others flatten out quickly, suggesting their dark matter is more diffusely spread. Even peculiar shapes in these curves, tiny kinks or plateaus, can betray past collisions or mergers, like cosmic scars etched into a galaxy's motion. The implications go far beyond individual galaxies. Rotation curves helped confirm that dark matter isn't just a Milky Way quirk, it's universal. From the smallest dwarf galaxies to the largest spirals, the same discrepancy between visible mass and gravitational pull persists. And when astronomers compare rotation curves to supercomputer simulations of the universe, the match is uncanny, but only if dark matter is included. Without it, virtual galaxies spin too slowly or tear themselves apart, a stark reminder of how essential this hidden ingredient is to the cosmic recipe. What's fascinating is how rotation curves keep challenging us. Some galaxies, like ultra-diffuse ones with barely any stars, rotate as if they're packed with dark matter, while others, like certain compact dwarfs, barely seem to need it at all. These outliers force scientists to refine their models, probing whether dark matter behaves differently in diverse environments or if new physics might be at play. Every new observation adds nuance to the story, turning rotation curves from simple graphs into rich narratives about how galaxies live, evolve, and interact. They're not just measurements, they're windows into the invisible architecture of the universe, reminding us that what we see is only a fraction of what's out there. Hidden in the hearts of nearly every galaxy, from the smallest dwarfs to the grandest spirals, lurks a monster, a supermassive black hole, so dense and powerful it bends the very fabric of space around it. These aren't just passive voids, they're dynamic engines shaping their galaxies in ways we're only beginning to understand. Take Sagittarius, a star, the Milky Way's own supermassive black hole. Though quiet now, its gravity orchestrates the motion of millions of stars, forcing them into frenetic orbits like bees around a hive. But when galaxies collide, these hidden giants awaken. As two galaxies merge, their black holes spiral toward each other, locked in a gravitational duel that can fling stars across space and unleash torrents of energy visible across the universe. The influence of these black holes goes far beyond their immediate surroundings. They regulate star formation like cosmic thermostats, heating surrounding gas with jets of radiation so intense they prevent it from cooling and collapsing into new stars. In some galaxies, like the brilliant quasars of the early universe, supermassive black holes turn their homes into beacons, outshining all their stars combined. Yet in others, they're nearly dormant, their presence revealed only by the frantic orbits of nearby stars. This duality, destructive yet creative, chaotic yet precise, makes them the universe's ultimate paradoxes. When two galaxies merge, their black holes face a fate as dramatic as the collision itself. Drawn together by gravity, they begin a slow, spiraling dance that can last millions of years, shedding energy in ripples of spacetime called gravitational waves. These waves, first detected by LIGO in 2015, are the universe's way of broadcasting these colossal encounters. Eventually, the black holes may collide, merging into a single, even more massive entity, an event so violent it sends shockwaves through the fabric of reality. The resulting gravitational waves would be strong enough to distort space itself, though by the time they reach us, the effect is subtler than the quiver of a leaf in the wind. What's astonishing is how these black holes shape their galaxy's evolution. Galaxies with overly active black holes often see star formation snuffed out, their gas reservoirs too heated to birth new stars. Others, like the Milky Way, strike a balance quiet enough to allow stellar nurseries to thrive, yet powerful enough to maintain order. Even the largest structures in the universe, like galaxy clusters, bear the imprint of their central black holes, whose outbursts carve vast cavities in the hot gas between galaxies. Studying these hidden conductors reveals a universe far more interconnected than we once thought. The growth of a black hole is tied to the growth of its galaxy, a symbiotic relationship forged over billions of years. By peering into the hearts of galaxies, both near and far, astronomers are uncovering the delicate balance between creation and destruction, between chaos and order, a balance held quite literally in the grip of the universe's most mysterious giants. Massive stars don't just light up galaxies, they sculpt them, wielding unimaginable power even in death. When these giants explode as supernova or unleash torrents of radiation during their lives, they don't fade quietly. Instead, they generate colossal galactic winds, hurricane-like outflows that blast gas and dust clear out of their home galaxies. Picture a candle not just flickering but blowing its own wax into space. These stellar behemoths reshape their surroundings on a cosmic scale. These winds aren't gentle breezes. They race at millions of miles per hour, carrying enough energy to fling entire star-forming regions into the void. Take the iconic starburst galaxy Messier 82, where stars are born in such frenzied numbers that their combined fury has created a superwind, a titanic funnel of hot gas shooting outward from its core. This wind stretches for tens of thousands of light years, a visible testament to the chaos unleashed by massive stars. But it's not just about destruction. These winds act like cosmic regulators, preventing galaxies from turning all their gas into stars too quickly. Without them, galaxies would burn through their fuel in a frenetic burst, leaving behind lifeless husks. Instead, the winds slow star formation, stretching out a galaxy's creative potential over billions of years. What's truly remarkable is how far these winds reach. Gas ejected from one galaxy can travel vast distances, eventually seeding neighboring galaxies with heavy elements forged in supernova. The oxygen we breathe, the iron in our blood, these atoms were likely hurled into space by ancient stellar explosions, carried on galactic winds until they found their way into new star systems. In this way, these outflows connect galaxies across time and space, weaving a web of shared chemistry. Scientists track these winds by looking for telltale signs: X-rays from superheated gas, ultraviolet light from ionized elements, or even distortions in the magnetic fields of intergalactic space. The James Webb Space Telescope has revealed winds in unprecedented detail, showing how they strip gas from galaxies like autumn winds tearing leaves from trees. Some outflows are so powerful they create vast bubbles in the surrounding intergalactic medium, while others leave behind intricate filamentary structures like cosmic graffiti etched into the void. Yet galactic winds aren't unstoppable. In dense galaxy clusters, the surrounding hot gas can act like a wall, forcing winds to stall and fall back, raining material back onto their home galaxies in a cycle of expulsion and return. This recycling process might explain why some galaxies, like our Milky Way, have periods of intense star formation followed by long quiet spells. Their own winds eventually circle back, fueling new bursts of creation. Understanding these outflows isn't just about mapping where gas goes, it's about decoding the delicate balance that keeps galaxies alive. Too little wind, and a galaxy chokes on its own star-forming frenzy. Too much, and it bleeds itself dry. Between these extremes lies the sweet spot where galaxies thrive, their growth paced by the very stars they birth. In the grand dance of the cosmos, galactic winds are the invisible currents that shape destinies, ensuring no galaxy burns too bright or fades too soon. Galaxy clusters are the universe's grandest stages, where thousands of galaxies whirl in an intricate dance choreographed by gravity. These colossal gatherings, like the Perseus cluster, aren't just random crowds, they're tightly bound cities of stars, held together by the immense pull of dark matter and threaded through with searing hot gas. Imagine a ballroom where every dancer is a galaxy, some spiraling gracefully, others darting in close encounters, all moving to the same gravitational rhythm. The Perseus cluster, one of the most massive structures we've observed, offers a front-row seat to this spectacle. Here, galaxies don't drift in isolation. They're constantly tugged by neighbors, their paths warped by the cluster's overwhelming gravity, their gas stripped away as they plunge through the superheated plasma between them. At the heart of these clusters lies a mystery, dark matter's invisible grip. Though we can't see it, its presence is undeniable. The way galaxies move within clusters defies the laws of physics unless there's far more mass than what's visible. Take the Bullet cluster, where two galaxy clusters collided in one of the most energetic events ever recorded. The visible gas, slowed by friction, lagged behind while the galaxies and the dark matter surrounding them raced ahead. This cosmic traffic jam left a clear fingerprint. The bulk of the cluster's mass wasn't where the gas glowed brightest, but where the galaxies sailed onward, guided by dark matter's unseen hand. But it's not just dark matter shaping these environments. The space between galaxies in a cluster is far from empty. It's filled with a thin, scorching gas, hotter than the core of a star. This gas emits X-rays, painting the cluster in a faint, eerie glow. As galaxies move through it, they experience a sort of cosmic headwind, their own gas stripped away like sand blown from a dune. This process, called ram pressure stripping, leaves some galaxies naked, their star-forming fuel ripped from them, turning them into quiet, red relics. The Virgo cluster, our nearest galactic metropolis, is littered with such galaxies, their once vibrant spirals now faded, their gas tails stretching far behind them like comet trails. Yet even in these dense, chaotic environments, there's order. Galaxies near a cluster's center tend to be older ellipticals, their stars orbiting in random directions, while spirals younger and gas-rich often linger at the edges, still falling into the cluster's gravitational embrace. Over billions of years, these spirals will be transformed, their gas stripped, their shapes distorted by tidal forces until they, too, join the red and dead population at the core. This isn't just destruction, it's evolution, a cycle as old as the universe itself. What makes clusters so fascinating isn't just their scale, it's what they reveal about the cosmos. By studying how galaxies behave in these extreme environments, astronomers can test theories about dark matter, gravity, and even the universe's expansion. Clusters act as magnifying glasses, bending light from more distant objects in a phenomenon called gravitational lensing, allowing us to peer farther into space than ever before. They're also time capsules, preserving clues about how the universe grew from a smooth, featureless expanse into the web of galaxies we see today. Every cluster tells a story of collisions, transformations, and the invisible forces that bind the cosmos together. And as we observe them, from the bustling Perseus cluster to the turbulent Coma cluster, we're not just watching galaxies dance, we're deciphering the universe's grandest ballet, one movement at a time. Edwin Hubble's groundbreaking discovery in the 1920s didn't just change astronomy, it rewrote our entire understanding of the cosmos. Peering through the lens of the Hooker telescope, he noticed something peculiar about distant galaxies. Their light was stretched, shifting toward the red end of the spectrum, as if the universe itself were pulling them away from us. But this wasn't just about galaxies moving through space, it was space itself expanding, carrying galaxies along like raisins in a rising loaf of bread. Hubble's observations revealed a universe in motion, one where every galaxy, cluster, and supercluster is caught in a vast, relentless flow, drifting apart on an ever-expanding cosmic dance floor. This motion, now known as the Hubble flow, isn't random. The farther a galaxy is from us, the faster it appears to recede, a relationship Hubble quantified with his famous law. Imagine standing in a crowd where everyone takes a step back for every meter they are from you. The person 1 meter away moves a little, but someone 10 meters back covers much more ground. That's how expansion works on a galactic scale, but here's the twist. It's not that galaxies are speeding through space. It's that the space between them is stretching, a subtle but crucial distinction. Light traveling through this expanding space gets stretched too, its wavelengths elongating into redshift, a cosmic fingerprint of the universe's growth. What's even more startling is how this expansion has changed over time. In the late 1990s, astronomers studying distant supernova made a jaw-dropping discovery. The universe isn't just expanding, it's accelerating. Some mysterious force, now called dark energy, appears to be pushing galaxies apart faster and faster, counteracting gravity's pull. Think of it like a dance where the floor keeps widening, forcing partners farther apart even as they try to move closer. Dark energy now makes up about 68% of the universe's total energy, dwarfing both visible matter and dark matter in its influence. The Hubble flow isn't just a backdrop to galactic motion, it's the dominant force shaping the universe's large-scale structure. Over billions of years, as space stretches, galaxy clusters grow more isolated, their local gravitational bonds the only thing holding them together against the tide of expansion. In the far future, distant galaxies will redshift beyond detection, their light stretched into oblivion, leaving any observers in our local group with a sky devoid of external galaxies. It's a haunting thought. The universe's expansion could one day render much of it invisible to us, a cosmic curtain falling on the grandest stage of all. Yet, even as the Hubble flow pulls galaxies apart, it leaves behind clues about the universe's origins. The pattern of expansion traces back to the Big Bang, carrying imprints of the universe's earliest moments. By measuring how galaxies move within this flow, scientists can probe the nature of dark energy, test theories of gravity, and even estimate the universe's age. Every redshifted photon, every distant supernova, adds another piece to the puzzle, helping us decode the story of an expanding cosmos, one where space itself is the ultimate dancer, and every galaxy moves to its rhythm. Dark energy is the universe's greatest enigma, an invisible force not just expanding space but accelerating its stretch, as if the cosmos itself is pressing harder on the gas pedal. Picture a balloon inflating, but instead of slowing down, it blows up faster and faster, its surface stretching so rapidly that dots drawn on it, galaxies in this metaphor, hurtle away from one another at ever-increasing speeds. This isn't just theoretical. In the late 1990s, two independent teams studying distant supernova made the same shocking discovery. The universe's expansion isn't slowing due to gravity, as everyone expected. It's speeding up. The culprit, a mysterious repulsive force dubbed dark energy, which now makes up a staggering 68% of the universe's total energy budget. What makes dark energy so puzzling is how it defies gravity's pull. Imagine a dance where two partners try to step closer, but the floor beneath them keeps widening faster than they can move. That's the reality for galaxies bound in clusters. Their local gravity keeps them together, but on cosmic scales, dark energy dominates, pushing clusters apart so forcefully that over time, even the tightest gravitational bonds may not hold. The implications are profound. If this acceleration continues, distant galaxies will eventually vanish from view, their light stretched beyond detectability, leaving future civilizations in our local group with a sky devoid of external galaxies, a lonely island universe. Yet dark energy's origins remain one of cosmology's biggest unsolved puzzles. Some theories suggest it's tied to the vacuum of space itself, a property Einstein once called the cosmological constant, before dismissing it as his greatest blunder. Others propose it's a dynamic field, like an anti-gravity version of the Higgs field, evolving over time. The truth, we don't know. What we do know is that dark energy's effects are etched into the cosmos. By studying baryon acoustic oscillations, frozen ripples in the distribution of galaxies from the early universe, scientists have mapped how dark energy has influenced large-scale structure over billions of years. These ancient sound waves, imprinted when the universe was a seething plasma, now serve as cosmic yardsticks, revealing how dark energy has stretched the fabric of space. The hunt to understand this force is driving some of astronomy's most ambitious projects. The Dark Energy Survey, the Euclid Space Telescope, and the upcoming Vera Rubin Observatory are all designed to probe dark energy's secrets, measuring its effects with unprecedented precision. Each observation brings us closer to answering existential questions. Will the universe expand forever, growing colder and darker until all galaxies are isolated? Or could dark energy's strength change, leading to a dramatic Big Rip that tears apart even atoms? For now, dark energy remains the ultimate wild card in cosmic evolution, an invisible hand rewriting the universe's fate, one accelerating galaxy at a time. The cosmic web is the universe's grand architecture, an intricate network of filaments woven from dark matter and gas, stretching across billions of light years like the veins of a colossal leaf. Picture it as a spider's silk on the scale of the cosmos, with galaxies strung along its threads like dewdrops, drawn together at intersections where massive clusters glow like cities in the night. This isn't just a static skeleton, it's a dynamic highway system guiding the motion of galaxies in a slow, gravitational current. Simulations like the Millennium Run have brought this hidden framework to life, tracing how galaxies slide along these filaments, funneled into dense knots where they collide, merge, and cluster in a celestial metropolis. What's astonishing is how this web shapes everything we see. Without it, galaxies would scatter randomly, drifting like ships without currents. Instead, they follow the web's invisible rails, pulled toward intersections where gravity's grip is strongest. The Virgo supercluster, home to our Milky Way, sits at the edge of one such junction, a local hub in the cosmic sprawl. But zoom out further, and the pattern repeats. The Laniakea supercluster, a sprawling river of galaxies spanning 500 million light-years, flows toward the Great Attractor, a gravitational focal point hidden behind the Milky Way's dust. The cosmic web's origins trace back to the Big Bang's aftermath, when tiny quantum fluctuations seeded the universe with slight density variations. Over billions of years, gravity amplified these ripples, pulling matter into filaments and leaving vast voids between them. Today, these voids are deserts, regions so empty that if you stood in one, the night sky would appear nearly black, with only the faintest glow of distant galaxies. Meanwhile, the filaments hum with activity, channeling gas into galaxies and feeding their growth like roots nourishing a tree. Dark matter is the unseen architect here. Though it doesn't interact with light, its gravitational pull sculpts the web's structure with ordinary matter, the gas and stars we can see simply following its lead. The web isn't just a backdrop, it's an active participant in galactic evolution. When galaxies slide along filaments, they accumulate gas, sparking bursts of star formation. Those that reach intersections may merge, their fates sealed by the web's relentless pull. Even now, the Milky Way is part of this flow, drifting toward the Virgo cluster at over 1 million miles per hour, riding the cosmic web's currents toward an inevitable collision course. Mapping this structure has required some of the most advanced tools in astronomy. Projects like the Sloan Digital Sky Survey have charted millions of galaxies, revealing the web's filamentary patterns in 3 dimensions. Meanwhile, supercomputers simulate its growth, from the universe's first flickers to the sprawling networks we see today. These models don't just match observations, they predict how the web will evolve. forecasting a future where filaments stretch thinner as dark energy pushes galaxies apart, leaving clusters isolated like islands in an expanding sea. The cosmic web is more than a map of where galaxies are. It's a blueprint for how they move, interact, and evolve. Every filament, every void tells a story of gravity's patient work, of dark matter's silent influence, and of the universe's relentless expansion. To understand the dance of galaxies, we must first trace the stage they dance upon, a stage woven from the fabric of space-time itself. Light from distant galaxies carries hidden messages about their motion, etched into its very color. When a galaxy races away from us, its light waves stretch, shifting toward the red end of the spectrum, a phenomenon called redshift. The faster it recedes, the redder its light appears. Conversely, galaxies hurtling toward us compress their light waves, creating a blue shift, a subtle but detectable blue tint. This isn't just about color, it's the universe's way of revealing its secrets through the Doppler effect, the same principle that makes an ambulance siren sound higher pitched as it approaches and lower as it speeds away. Edwin Hubble's groundbreaking observations in the 1920s hinged on this very concept. By measuring the redshift of distant galaxies, he discovered a startling pattern. The farther a galaxy was from Earth, the faster it appeared to be receding. This relationship, now known as Hubble's law, became the cornerstone of our understanding of cosmic expansion. But redshift isn't just a tool for mapping the universe's growth, it's also a time machine. The light from extremely distant galaxies has been traveling for billions of years, its redshift acting like a cosmic odometer, telling us not just how far the galaxy is, but how long its light has journeyed to reach us. Blue shift, though rarer, is equally revealing. The Andromeda galaxy, for instance, shows a slight blue shift because it's on a collision course with the Milky Way. By measuring this shift, astronomers can calculate its velocity with astonishing precision, around 250,000 miles per hour toward us. These shifts aren't limited to entire galaxies either. Within a single galaxy, stars and gas clouds exhibit their own Doppler signatures, allowing scientists to map rotations, detect hidden orbital patterns, and even uncover the gravitational fingerprints of unseen dark matter. What's truly remarkable is how these measurements intertwine. Redshift doesn't just indicate motion, it also correlates with distance, thanks to the universe's expansion. The more distant a galaxy, the more space has stretched during the light's journey, amplifying its redshift. This dual role makes redshift a powerful tool for constructing three-dimensional maps of the cosmos, revealing the large-scale structure of filaments and voids that define the cosmic web. Without it, we'd be blind to the universe's architecture, seeing galaxies as static points rather than dynamic players in an expanding tapestry. Yet interpreting these shifts isn't always straightforward. Gravitational redshift, caused by light climbing out of a massive object's gravitational well, can mimic the Doppler effect, requiring careful analysis to disentangle the two. Even the expansion of space itself adds complexity. While nearby galaxies show Doppler-like redshifts dominated by their local motion, the most distant ones are carried away by the stretching of space, their light stretched not because they're moving through space, but because space itself is growing beneath them. From revealing the universe's expansion to predicting galactic collisions, redshift and blueshift are more than just color changes, they're the language of cosmic motion, a lexicon written in light. Every shifted wavelength tells a story of velocity, distance, and the relentless pull of gravity, offering a glimpse into the universe's past, present, and future. And as telescopes grow more sensitive, these subtle spectral clues will continue to unveil the universe's deepest secrets, one photon at a time. Stars are more than just points of light, they're cosmic time capsules, each one holding clues to the galaxy's violent collisional past. Every star's chemical makeup tells a story about when and where it was born, while its motion betrays gravitational upheavals from ancient mergers. Think of it like tracing your ancestry through DNA, except instead of cheek swabs, astronomers use starlight. When stars form from the same gas cloud, they inherit identical chemical fingerprints, specific ratios of elements like oxygen, iron, and rare earth metals. Over time, galactic collisions scatter these stellar siblings, but their shared chemistry and orbital paths remain, allowing scientists to piece together lost chapters of a galaxy's history like pages torn from a book. The Milky Way's halo, that vast spherical cloud of stars surrounding our galaxy's disk, is a treasure trove for these celestial archaeologists. Here, stars don't move in orderly orbits. They loop and dive chaotically, their paths etched by past encounters. Some, like those in the Helmi stream, trace wild, looping trajectories that betray their origin as part of a dwarf galaxy devoured by the Milky Way over 8 billion years ago. Others, like the stars in the Gaia sausage structure, orbit almost perpendicular to the galactic plane, the remnants of a head-on collision with a galaxy 1/10 the Milky Way's size. These aren't just random stars, they're survivors of a cosmic demolition derby, their motions frozen in time like dancers caught mid-step when the music stopped. None of this would be visible without missions like Gaia, the European Space Agency's star mapping powerhouse. Since 2014, Gaia has charted the positions, motions, and chemical compositions of over 1.8 billion stars, creating the most detailed 3D atlas of our galaxy ever made. Its data reveals stellar streams, rivers of stars winding through the Milky Way that were once independent galaxies. The Sagittarius stream, for example, stretches over 300,000 light-years, a shimmering ribbon of stars torn from a dwarf galaxy currently being digested by the Milky Way. By tracking these streams backward in time, astronomers have reconstructed a history of galactic cannibalism stretching back over 10 billion years. What's astonishing is how much these stellar fossils reveal about dark matter. When a small galaxy falls into the Milky Way, its stars get pulled apart, but the dark matter halo surrounding it stays intact, subtly warping the orbits of nearby stars. By studying these distortions, scientists have mapped the Milky Way's own dark matter halo, uncovering its lumpy, asymmetrical shape, proof that our galaxy grew not smoothly, but through violent mergers. Even the Milky Way's disk bears scars, ripples and wrinkles in its spiral arms, likely caused by a close encounter with the Sagittarius dwarf galaxy hundreds of millions of years ago. This isn't just about the past, it's about the future too. As Gaia continues its survey, it's uncovering new stellar streams, some so faint they're barely detectable. These could be the edges of dwarf galaxies we've yet to discover, or remnants of mergers so ancient their parent galaxies are long gone. Every new data release adds pieces to the puzzle, revealing how the Milky Way grew from a tiny seed in the early universe to the grand spiral we see today. And beyond our galaxy, similar techniques are being used to decode the histories of Andromeda and other nearby galaxies, proving that no island in the universe is truly isolated. Everything is connected through gravity's unbreakable thread. Galactic archaeology does more than reconstruct history, it reshapes our understanding of how galaxies evolve. Those faint streams of stars aren't just relics, they're proof that galaxies aren't born massive, they grow by consuming their neighbors, their histories written in the chemistry and motion of the stars they've stolen. And as we uncover more of these stories, we're not just learning about the Milky Way, we're reading the autobiography of the universe itself. Simulating the universe is like building the ultimate cosmic time machine, one where scientists can rewind, fast forward, and replay the dance of galaxies with astonishing precision. At the heart of this endeavor are supercomputers, crunching unimaginable amounts of data to recreate billions of years of galactic evolution in mere weeks. Take the Illustris TNG project, a groundbreaking simulation that models not just stars and gas, but the invisible scaffolding of dark matter that shapes everything. Picture a virtual universe where galaxies form, collide, and evolve according to the laws of physics, their fates dictated by equations rather than chance. These aren't just video game graphics, they're mathematical mirrors of reality, so accurate they can predict the distribution of galaxies we haven't even discovered yet. What's truly remarkable is how these simulations reveal the hidden rules of galactic behavior. By tweaking variables like the strength of dark matter's pull or the rate of star formation, scientists can test theories against real-world observations. For instance, when simulations suggested that galaxies should have far fewer satellite galaxies than we observe, it led to a startling realization: our models of dark matter were incomplete. Revised simulations incorporating warm, dark matter particles moving at higher speeds suddenly matched reality, offering clues to one of cosmology's biggest mysteries. It's like tuning a musical instrument until every note aligns with the symphony of the cosmos. These virtual universes also let us witness events too slow or distant to study directly. Want to watch the Milky Way and Andromeda collide? Simulations like those from the evolution and assembly of Galaxies and their environments, Project Eagle for short, can show you the entire billion-year spectacle in minutes. They reveal how the two spirals will twist into a single elliptical galaxy, their stars scattering like sparks from a firework. But the real magic lies in the details: tidal tails stretching across space, bursts of newborn stars ignited by compressed gas, even the supermassive black holes at their cores spiraling toward a cataclysmic merger. Yet simulations aren't just about predicting the future, they're detectives uncovering the past. By comparing virtual galaxies to ancient ones observed by the James Webb Space Telescope, astronomers can piece together how the first galaxies formed. Some simulations suggest early galaxies grew not just by merging, but by sucking in vast rivers of cold gas from the cosmic web, a process called cold accretion. Others reveal how supernova explosions might have blown gas out of fledgling galaxies, temporarily halting star formation. Without these digital laboratories, we'd be left guessing how the universe transformed from a smooth soup of particles into the intricate web we see today. The challenges are as immense as the simulations themselves. Even the most advanced models must simplify reality to avoid calculations that would take centuries. Gas dynamics, magnetic fields, the chaotic birth of stars, each requires approximations, but as supercomputers grow more powerful, so do the simulations. Projects like Frontier, the world's fastest supercomputer, are pushing boundaries, resolving individual stars within galaxy-sized calculations for the first time. Soon we may simulate not just galaxies, but the planets within them, tracing the cosmic journey of every atom from the Big Bang to the present. What's at stake isn't just academic curiosity. These virtual universes help interpret real observations, like puzzling galactic collisions or strange stellar streams. They guide telescopes, telling astronomers where to look for hidden galaxies or faint remnants of ancient mergers. And they prepare us for future discoveries, like the gravitational waves from merging black holes that simulations first predicted decades before LIGO detected them. In the end, cosmological simulations are more than tools, they're windows into the universe's deepest secrets, letting us explore not just how galaxies move, but why they move the way they do. Every line of code is a step closer to understanding the grand choreography of the cosmos. Magnetic fields are the invisible conductors of galactic symphonies, weaving through galaxies with a subtle yet profound influence on their motion and evolution. While gravity and dark matter dominate the cosmic dance, these fields, threaded through interstellar space like an intricate web, play a crucial backstage role. Picture a galaxy not just as a collection of stars and gas, but as a dynamic arena where magnetic forces twist and channel charged particles, shaping the very fabric of star-forming regions. In the Milky Way, for instance, magnetic fields align dust grains, polarizing starlight in ways that reveal their presence, while also guiding the paths of cosmic rays, high-energy particles racing through space at nearly the speed of light. These fields don't just linger passively, they actively sculpt galactic environments. Take the iconic pillars of creation in the Eagle Nebula. Here, magnetic fields help stabilize towering columns of gas against collapse, slowing the birth of new stars and extending the life of these cosmic nurseries. Elsewhere, fields can compress gas clouds, accelerating star formation or even funneling material towards supermassive black holes at galactic centers, fueling their growth. During collisions between galaxies, magnetic fields become even more dramatic, stretching and tangling like spaghetti in a whirlpool, their lines snapping and reconnecting in bursts of energy that heat surrounding gas and alter the course of stellar evolution. The challenge has always been mapping these elusive forces. Traditional telescopes can't see magnetic fields directly, but their fingerprints are everywhere in the way dust grains align, how cosmic rays spiral along field lines, or how polarized light twists as it travels through interstellar space. Enter the Square Kilometre Array, or SCAR, a next-generation radio telescope set to revolutionize our understanding. With thousands of antennas spread across 2 continents, the SKA will detect the faint radio waves emitted by electrons spiraling around magnetic fields, creating the most detailed maps yet of their structure and strength. These observations could reveal how fields influence galaxy-scale winds, shape spiral arms, or even seed the cosmic web itself. What's truly fascinating is how magnetic fields bridge scales, from the smallest star-forming clouds to the largest galactic collisions. In the Antennae galaxies, for example, colliding gas clouds generate shockwaves that amplify magnetic fields, which in turn steer the flow of material, determining where new stars will ignite. Simulations now suggest that without these fields, galaxies might look radically different, their gas distributions uneven, their star formation rates erratic. They're not just bystanders, they're active players in the cosmic ballet, nudging galaxies toward their destinies one charged particle at a time. As we peer deeper into the universe, magnetic fields emerge as silent architects of galactic structure, their influence woven into every spiral arm, every stellar nursery, every collision. With tools like the SKA, we're on the verge of uncovering their full role, not just as bit players, but as directors of the grandest performance in the cosmos. Galactic fountains are the universe's recycling system, a breathtaking cycle where gas is blasted into the depths of space, only to rain back down, seeding galaxies with the ingredients for new stars and planets. Picture a supernova explosion, one of the most violent events in the cosmos, hurling waves of gas outward at millions of miles per hour. This material doesn't just vanish, it surges into the galaxy's halo, a vast, diffuse cloud of gas and dust surrounding the disk, where it lingers like steam rising from a boiling pot. Over time, the gas cools, condenses, and cascades back down in shimmering rivers, a process astronomers poetically call a galactic fountain. These flows aren't just beautiful, they're essential, ensuring galaxies don't exhaust their star-forming fuel too quickly. Take the Milky Way. Observations reveal towering plumes of gas rising thousands of light-years above and below the galactic plane, evidence of countless supernovae pumping energy into the interstellar medium. As this hot gas ascends, it carries heavy elements forged in stellar cores: carbon, oxygen, iron, sprinkling them into the halo like cosmic fertilizer. When the gas eventually cools and falls back, it brings these enriched materials with it, providing the raw ingredients for rocky planets and even life itself. Without this cycle, galaxies would either burn through their gas in a frenzied burst of star formation or stagnate, their interstellar medium growing stale and inert. These fountains don't just recycle, they regulate. By venting hot gas into the halo, supernova prevent runaway star formation, acting like a pressure valve on a cosmic scale. In starburst galaxies, where stars are born at breakneck speeds, the fountains work overtime, ejecting gas so violently it might never return, leaving the galaxy red and dead. In quieter spirals like the Milky Way, the balance is just right enough outflow to temper star formation, but enough return to sustain it over billions of years. The mechanics of these flows are incredibly complex. Gas doesn't fall back uniformly. It clumps into vast filamentary structures, colliding with other streams in midair, triggering shock waves that ripple through the galactic disk. Telescopes like the Hubble Space Telescope and the Chandra X-ray Observatory have caught glimpses of these processes, spotting gas clouds glowing in ultraviolet and X-rays as they heat and cool. Meanwhile, simulations like those from the Fire Project feedback in realistic environments show how these fountains interact with dark matter halos, magnetic fields, and even neighboring galaxies, weaving a tapestry of feedback loops that shape galactic evolution. What's truly astonishing is how these fountains connect small-scale events to galaxy-wide phenomena. A single supernova might seem insignificant, but collectively, these explosions drive winds that sculpt entire galaxies. In the early universe, galactic fountains may have been even more powerful, ejecting gas so far it escaped the galaxy entirely, seeding the intergalactic medium with the elements needed for future generations of stars. Today, they're quieter but no less vital, ensuring galaxies like ours continue to evolve, adapt, and thrive. Studying these flows isn't just about understanding the past, it's about predicting the future. By measuring how gas cycles in and out of galaxies, astronomers can forecast how long star formation will last, when galaxies will fade, and how the universe's chemical makeup will change over time. Galactic fountains are more than just recycling plants. They're the heartbeat of galaxies, pulsing with the rhythm of stellar life and death, a rhythm that echoes across the cosmos. The Milky Way isn't drifting through space aimlessly. It's being pulled, along with thousands of neighboring galaxies, toward a gravitational enigma known as the Great Attractor. Lurking around 250 million light-years away, this invisible behemoth exerts a force so powerful it bends the paths of entire galaxy clusters, including our own local group, toward it at speeds exceeding 1,000,000 miles per hour. Yet for decades, its true nature remained obscured, hidden behind the thick dust and stars of the Milky Way's disk, a cosmic blind spot astronomers call the zone of avoidance. It's as if we're sailing toward a mountain shrouded in fog, sensing its presence but unable to glimpse its shape. Early observations in the 1970s and 80s revealed the first clues. Scientists mapping the motion of galaxies noticed something peculiar. Everything in our corner of the universe, from the Milky Way to the Virgo cluster, was streaming toward a single point in the constellation Centaurus. The sheer scale of this motion defied explanation. Known concentrations of mass, like the Virgo supercluster, couldn't account for the pull. There had to be something more, something massive and hidden, tugging at us from the shadows. The Great Attractor became astronomy's ultimate tease, a gravitational signature without a visible source. Breakthroughs came when astronomers peered through the galactic dust using instruments like NASA's Cosmic Background Explorer and the Parkes Radio Telescope. What they found was both surprising and humbling. The Great Attractor isn't a single, unimaginably dense object, but a sprawling confluence of mass, likely the heart of the Laniakea supercluster, a web of galaxies spanning 500 million light-years. Here, countless galaxy clusters, swathed in dark matter, create a gravitational well so deep it bends the flow of the cosmic web itself, drawing galaxies inward like water spiraling down a drain. Yet even this revelation left puzzles unsolved. The Great Attractor's pull is stronger than Laniakea's visible mass suggests, hinting at even denser structures beyond it. Some theories point to the Shapley supercluster, a staggering collection of galaxies 650 million light-years away, as the true mastermind behind our motion. Others propose that the Great Attractor is just one node in a vast, unseen river of dark matter, a current in the cosmic web guiding galaxies toward regions we've yet to map. Unraveling this mystery isn't just about satisfying curiosity, it's a key to understanding our place in the universe. The Great Attractor's influence reveals how dark matter sculpts large-scale flows, how superclusters evolve, and even how the universe's expansion might vary locally. Every new observation, from infrared surveys to X-ray mappings of hot gas, peels back another layer of the enigma. And as telescopes grow more advanced, we're not just solving a cosmic riddle, we're learning how to read the invisible currents that carry galaxies, including our own, through the vast ocean of space. Galaxies are often thought of as solitary wanderers, each charting its own course through the cosmos, but sometimes they move in eerie unison, as if guided by an unseen conductor. The Leo Ring is one of the most striking examples, a colossal, near-perfect circle of hydrogen gas stretching across 650,000 light-years, orbiting a pair of galaxies with uncanny precision. This isn't just a cosmic oddity, it's a puzzle that defies conventional explanations. Normally, such a delicate structure would be torn apart by gravity or distorted by galactic collisions, yet the Leo Ring persists, its gas swirling in serene synchrony. Astronomers have proposed wild theories to explain it. Perhaps it's the remnant of an ancient galactic collision, a smoking gun from a billion-year-old encounter that left debris spinning in perfect equilibrium. Or maybe it's fed by dark matter, its invisible grip orchestrating the gas into this improbable formation. This isn't the only example of cosmic choreography. In the Coma cluster, hundreds of galaxies move together in a coordinated flow, their velocities aligned like birds in a flock. Simulations suggest these synchronized motions could be echoes of the early universe, when galaxies first formed along vast filaments of dark matter, inheriting their motion from the primordial currents of the cosmic web. Other cases, like the dancing dwarfs around Andromeda, small galaxies orbiting in a bizarrely flat plane, hint that our understanding of galactic dynamics might be missing a crucial piece. Could dark matter be distributed in ways we haven't yet imagined? Or are we seeing the ghostly fingerprints of long-forgotten interactions, imprinted billions of years ago? What makes these synchronized systems so valuable is how they stress-test our theories. Every anomaly, every galaxy moving out of step, forces scientists to rethink assumptions. The Leo Ring, for instance, challenges models of gas dynamics, suggesting that interstellar material might be more resilient or influenced by subtler forces than we thought. Meanwhile, the coordinated motions in clusters like Coma probe the limits of dark matter's role. Does it merely provide the scaffolding for galaxies, or does it actively nudge them into alignment over time? Even the Milky Way has its own rhythm. satellite galaxies like the Large and Small Magellanic Clouds appear to orbit in a plane that shouldn't be stable, yet it persists, defying expectations. Unraveling these mysteries isn't just about cataloging oddities, it's about refining the rules that govern all galaxies. By studying synchronized systems, astronomers can calibrate their simulations, testing how factors like dark matter halos, tidal forces, or even magnetic fields might lock galaxies into these strange, harmonious dances. The answers could reshape everything from our understanding of galaxy formation to the fate of our own cosmic neighborhood. After all, if galaxies can move in such precise concert, what else might the universe be hiding in plain sight? The next generation of telescopes promises to revolutionize our understanding of galactic motion, peeling back cosmic mysteries with unprecedented clarity. Imagine the James Webb Space Telescope, already transforming astronomy with its infrared gaze, now turning its golden mirrors toward the faintest stellar streams, remnants of ancient galactic collisions. These delicate filaments, too dim for previous telescopes to resolve, hold secrets about how galaxies grow through mergers over billions of years. Webb's sensitivity lets it detect the chemical fingerprints of stars in these streams, revealing whether they were ripped from dwarf galaxies or forged in the violent wakes of past collisions. But it's not just about seeing farther. Webb's sharp vision can pinpoint individual stars in distant galaxies, tracking their motions to map the invisible tug of dark matter with precision never before possible. On the ground, the Extremely Large Telescope, or ELT, will take this quest to new heights literally. With a mirror spanning 39 meters, this behemoth will capture images 16 times sharper than Hubble's, dissecting galactic nuclei where supermassive black holes lurk. By measuring how stars whip around these voids, the ELT could reveal how black holes influence galactic orbits, settling debates about whether they act as anchors or disruptors in the cosmic dance. Its spectrographs will also detect redshift in galaxies so distant their light has traveled over 13 billion years, letting us watch the universe's expansion accelerate in real time, a direct window into dark energy's relentless push. Then there's the Nancy Grace Roman Space Telescope, set to launch later this decade. Unlike Webb's focused gaze, Roman will survey vast swaths of sky, mapping millions of galaxies in unprecedented detail. Its wide field view is perfect for spotting rare galactic interactions, like slow-motion collisions or flyby encounters where galaxies graze each other, leaving gravitational scars. Roman's true power lies in its ability to measure weak gravitational lensing subtle distortions in galaxy shapes caused by dark matter's invisible bulk. By analyzing these distortions across cosmic time, scientists hope to crack dark energy's code. Is it constant, or does its strength vary, altering the universe's fate? These instruments won't work alone. Together with advanced radio telescopes like the Square Kilometre Array, which traces magnetic fields threading through galaxies, and gravitational wave detectors like LISA, sensing the ripples from colliding black holes, we're building a multidimensional toolkit. Each observatory adds a piece to the puzzle. Webb revealing stellar chemistry, ELT tracking motions, Roman mapping large-scale structure. The synergy is key. While Webb might spot a galaxy distorted by dark matter, the ELT could measure its star's velocities, confirming the hidden mass's distribution. What excites scientists most are the surprises. Every leap in observational power has unveiled phenomena we didn't predict, from dark energy's discovery to galaxies that defy rotation rules. With these new tools, we might find galaxies moving in lockstep across vast distances, evidence of exotic dark matter interactions, or even entirely new classes of objects shaping galactic motion. The universe's dance is far more intricate than we've glimpsed, and soon we'll see the choreography in full. the universe's grand dance of galaxies won't last forever. Over trillions of years, the vibrant cosmic ballet we see today will slow to a whisper, its performers fading one by one. Picture a ballroom where the music gradually dies. First, the gas needed to birth new stars will run dry, leaving galaxies to burn through their remaining fuel. Spirals like the Milky Way, once vibrant with stellar nurseries, will grow dimmer, their blue giant stars flickering out first, leaving behind cooler, redder embers. Elliptical galaxies, already packed with aging stars, will darken further, their populations dwindling as stars expire in slow succession. Even galactic mergers, the dramatic collisions that reshape cosmic landscapes, will become rare events. As the universe expands, galaxies will grow isolated, their nearest neighbors too distant for gravity to pull them together. The dance partners will drift apart, leaving behind solitary giants in an ever-cooling cosmos. Dark energy, that mysterious force accelerating the universe's expansion, will become the ultimate choreographer of this bleak finale. Current models suggest that in about 150 billion years, all galaxies beyond our local group will have redshifted beyond visibility, their light stretched past the edge of detectability. The night sky, once teeming with distant galaxies, will appear empty, a void punctuated only by the dim glow of nearby stars. Over even longer timescales, dark energy's grip may tighten further. In one terrifying scenario, the Big Rip, its strength could overcome gravity's hold entirely, tearing apart galaxy clusters, then galaxies themselves, and finally even stars and atoms, reducing all matter to unbound particles adrift in an infinite, lifeless expanse. Yet even this grim fate holds pockets of intrigue. Black holes, the universe's last surviving structures, may outlive stars by unimaginable eons. Supermassive black holes at galactic centers will continue their slow feast, consuming any remaining matter in their grasp. Over time, even these titans will evaporate via Hawking radiation, their energy leaking away in faint particle streams, a process so slow that the last black hole might not vanish until 10 to the power of 100 years have passed. By then, the universe will be a frigid, near-empty void, its temperature approaching absolute zero, its energy nearly uniform. The dance of galaxies will be a distant memory, preserved only in the faintest quantum fluctuations, if at all. But for now, the cosmos thrums with motion. Galaxies spin, collide, and merge, stars ignite and fade. Dark matter's invisible threads pull everything into an intricate, ever-changing web. Every observation, from the faintest stellar stream to the most violent galactic collision, adds to our understanding of this dynamic era. We're living in the universe's golden age of structure, a fleeting window where galaxies shine bright enough to study, and their motions tell stories spanning billions of years. The dance may not last forever, but for us here now, it's a spectacle without equal, offering endless mysteries to unravel and marvels to behold. You don't need a telescope or a degree in astrophysics to witness the dance of galaxies. Modern technology puts the cosmos at your fingertips. NASA's Eyes on the Solar System isn't just for exploring planets. It's a virtual playground where you can simulate galactic collisions with a few clicks. Picture this: you're at the controls, sending Andromeda hurtling toward the Milky Way, watching as gravity twists their spiral arms into chaotic ribbons of starlight. The simulation isn't just eye candy, it's built on real physics, using data from Hubble and other telescopes to recreate the forces shaping our universe. Adjust the angle, speed, or even the galaxy sizes, and watch how tiny changes alter the cosmic outcome. It's like having a universe-sized science lab in your browser, where you can test theories and witness billion-year processes unfold in seconds. For those who prefer hands-on discovery, citizen science projects like Galaxies turn volunteers into cosmic detectives. Here, everyday people help classify galaxies from telescope images, flagging oddities like colliding spirals or rare ring-shaped galaxies that might otherwise go unnoticed. Since its launch, Galaxy Zoo has led to groundbreaking discoveries, including Hannes Voorwerpen, a mysterious green blob of gas illuminated by a long-dead quasar spotted by a Dutch schoolteacher. These projects don't just crowdsource labor, they tap into the power of human intuition, proving that fresh eyes can spot patterns algorithms miss. Over 1 million participants have contributed, proving that galactic research isn't just for professionals, it's a shared adventure. Want to dive deeper? Tools like Universe Sandbox let you manipulate gravity itself, creating custom star systems or recreating historic events like the Milky Way's ancient collision with the Gaia Enceladus galaxy. Drop a black hole into a virtual galaxy and watch stars scatter like marbles. Tweak dark matter's influence and see how it alters galactic rotation curves, all while real-time physics calculations run beneath the surface. These platforms aren't just games, they're bridges between curiosity and understanding, demystifying complex concepts through interactivity. Even social media has become a window into galactic motion. Apps like Space Engine generate entire universes procedurally, allowing users to fly through photorealistic galaxies, each rendered with scientific accuracy. Zoom into a supermassive black hole's event horizon, then pivot to watch galaxies swirl in the Virgo cluster, all while learning about the forces at play through embedded tutorials. Meanwhile, YouTube channels like PBS Spacetime and Kurzgesagt pair these tools with animations, breaking down galactic dynamics into bite-sized, visually stunning lessons. The beauty of these resources is how they transform abstract concepts into tangible experiences. A textbook might describe tidal tales as gravitationally stripped stellar streams, but watching them form in a simulation, seeing stars stretch like taffy as galaxies collide, makes the phenomenon unforgettable. Whether you're a student, an amateur astronomer, or just someone who's ever looked up and wondered, these tools invite you to step into the universe's grand dance, not as a spectator, but as a participant. The cosmos has never been closer or more alive. Many people imagine galaxies zooming through space like bumper cars in a cosmic arena, chaotic, unpredictable, and destined for explosive collisions. But the reality is far more elegant and far less destructive. Galactic motion isn't random. It follows precise gravitational choreography, with every spiral, elliptical, and dwarf galaxy tracing paths shaped by dark matter, neighboring masses, and the expansion of space itself. And when galaxies do interact, it's less like a head-on crash and more like two ghosts passing through each other, their stars so distant that direct collisions are almost impossible. One of the biggest misconceptions is that galactic collisions spell doom for stars. In truth, space is so vast that even when galaxies merge, their stars rarely, if ever, collide. A galaxy like Andromeda, hurtling toward the Milky Way at 250,000 miles per hour, might seem like a cosmic wreck waiting to happen. But consider this, the average distance between stars in a galaxy is about 5 light-years. That's roughly 30 trillion miles of emptiness between stellar neighbors. When Andromeda and the Milky Way finally meet, their stars will glide past one another like two swarms of fireflies in the night, their individual paths barely disturbed. Another myth is that galaxies move in straight lines like bullets fired through space. In reality, their trajectories are curved, sculpted by the gravitational pull of nearby clusters and the dark matter scaffolding that weaves through the cosmos. The Milky Way, for example, isn't just drifting aimlessly, it's orbiting the center of the local group, a collection of galaxies bound together by mutual gravity. Even as dark energy pushes galaxies apart on cosmic scales, local clusters remain tightly knit, their members dancing in slow, looping orbits around shared centers of mass. Some also assume that when galaxies collide, they explode in a blaze of light and destruction. While mergers do trigger bursts of star formation as gas clouds compress, the process is far slower and more nuanced than Hollywood depictions suggest. The Antennae galaxies, a famous merging pair, have been entwined for hundreds of millions of years, their long, luminous tails stretching across space like celestial brushstrokes. Yet despite the spectacle, most stars continue their orbits undisturbed, their lives barely impacted by the gravitational turmoil around them. Finally, there's the idea that galaxies are solid, unchanging structures like frozen pinwheels suspended in space. Nothing could be further from the truth. Galaxies are dynamic, evolving entities, constantly reshaped by internal forces and external encounters. Spiral arms aren't fixed, they ripple and reform like waves in a pond. Stars migrate across galactic disks over billions of years, and supermassive black holes at galactic centers flare up, then quiet down, their outbursts sending shockwaves through surrounding gas. Understanding these truths transforms how we see the cosmos. Galactic interactions aren't violent smash-ups, they're slow, graceful ballets, where gravity does the heavy lifting and stars weave through the chaos unscathed. Far from being catastrophic, mergers are creative acts, recycling gas into new generations of stars and forging galaxies into entirely new shapes. The next time you look up at Andromeda, remember, its inevitable collision with the Milky Way won't be an ending, it'll be a rebirth, another step in the universe's endless dance of creation and change. The universe isn't just a visual spectacle, it's a symphony waiting to be heard. Scientists have discovered that by translating cosmic data into sound, hidden patterns emerge, revealing secrets our eyes alone could never catch. Take the Perseus cluster, a massive gathering of galaxies over 250 million light-years away. At its heart, a supermassive black hole churns, sending ripples through the surrounding hot gas. These ripples aren't silent. When scaled up 57 octaves to match human hearing, they resonate as a deep, haunting B-flat, a note so low it's nearly beyond our perception. This isn't just artistic interpretation, it's physics made audible, a direct translation of pressure waves into something we can feel in our bones. Sonification, the process of turning data into sound, does more than create eerie space music. It exposes rhythms and structures invisible in graphs or images. When researchers mapped the orbits of stars in the Milky Way to musical notes, for instance, they uncovered harmonies that hinted at long-lost galactic collisions. Fast-moving stars became high-pitched tones, while slower, older stars produced deeper bass notes. Played together, these sounds revealed a celestial choir, with off-key outliers betraying stars stolen from smaller galaxies during ancient mergers. What looks like scattered dots on a telescope image becomes, through sound, a story of cosmic theft and gravitational upheaval. Even the remnants of the Big Bang have a voice. The cosmic microwave background, the afterglow of the universe's birth, has been sonified into a shimmering drone, its tiny temperature fluctuations transformed into delicate pitch variations. Listen closely and you'll hear the seeds of all future structure, the faint imprint of density waves that would one day grow into galaxies. This isn't just poetry, it's a tool. Astronomers working with visual impairments use these sonic maps to hear galaxy distributions, while others find that subtle patterns in pitch or rhythm reveal anomalies missed by traditional analysis. A sudden crescendo might mark a shock wave from a supernova, or a repeating motif could hint at the spin of a distant pulsar. The beauty of this approach lies in its accessibility. You don't need a PhD to feel the difference between the eerie, pulsating tones of a black hole's accretion disk and the bright, staccato notes of a young star cluster. Projects like NASA, A Universe of Sound, invite the public to explore these sonic landscapes, from the whistling solar wind to the deep, resonant hum of galaxy clusters. It's a reminder that the cosmos speaks in more ways than one, and sometimes closing your eyes is the best way to see. The dance of galaxies unfolds on a stage so vast it dwarfs human history. But as we reach out to study these celestial wonders, we're forced to ask, do we have the right to intervene? The ethics of space exploration aren't just about rocket launches and telescope arrays. They're about confronting our responsibility to a universe that existed billions of years before us. Consider the pristine rings of Saturn or the delicate spiral arms of distant galaxies. Should they be treated as cosmic heritage sites, off-limits to human alteration, or are they frontiers waiting to be shaped by our curiosity? This tension between preservation and progress isn't hypothetical. Plans already exist to mine asteroids, deflect comets, and even terraform Mars, actions that could permanently alter the solar system's natural balance. The Outer Space Treaty of 1967 laid early groundwork, declaring celestial bodies the province of all mankind and banning national claims. Yet loopholes abound. While no country can own the moon, corporations can extract its resources. Private ventures now eye water ice in lunar craters and precious metals in asteroid belts, sparking debates. If a company profits from space resources, who benefits and who decides the environmental cost? The scars of earthly exploitation loom large. Radioactive debris from satellite collisions already litters low Earth orbit, creating dangerous debris fields. Without safeguards, could galaxies become the next backdrop for unchecked industrial expansion, their beauty sacrificed for platinum group metals or helium-3? Philosophically, the question cuts deeper. If life exists elsewhere, even microbial, does humanity have a moral duty to avoid contamination? NASA planetary protection protocols treat Mars like an archaeological dig, sterilizing probes to prevent Earth microbes from polluting potential ecosystems. But as ambitions grow, so do risks. Imagine a future where terraforming engineers accidentally smother native Martian life under domes of imported algae. Would that be progress or a cosmic crime? Some argue that intelligence confers responsibility, that as the only known species capable of stewardship, we must protect celestial phenomena as we've failed to protect Earth. Others counter that survival demands expansion, that clinging to one planet is riskier than adapting others. The dilemma extends beyond our solar system. Breakthrough Starshot's plan to send microprobes to Alpha Centauri raises thorny questions. If we dispatch tiny spacecraft to other star systems, could we unknowingly invade a civilization's equivalent of a backyard? Even passive observation carries ethical weight. SETI searches for extraterrestrial signals assume aliens want contact, but what if our listening breaches a galactic equivalent of privacy? Indigenous cultures on Earth often view celestial bodies as sacred. Might advanced civilizations hold similar beliefs about their local stars? Striking a balance requires global cooperation rarely seen on Earth. The Moon Agreement of 1979, which proposed sharing space resources equitably, was rejected by every major spacefaring nation. Today's Artemis Accords, led by the US, prioritize sustainable exploration but lack enforcement. Meanwhile, satellite megaconstellations like SpaceX's Starlink already disrupt astronomical observations, their glare drowning out faint galactic signals. Without binding frameworks, the cosmos risks becoming a free-for-all, its wonders commodified, its silence shattered. yet there's hope in the stars themselves. Galaxies teach patience, their slow dances measure time in billions of years, a reminder that haste is human, not universal. Perhaps our role isn't to conquer or preserve, but to learn humility. The universe thrived long before us, it will endure long after. Our task is to tread lightly, to study without scarring, and to ensure that when future generations look up, they see not just our footprints, but the untouched beauty of a cosmos that belongs to no one and everyone. The dance of galaxies is more than just a cosmic spectacle. It's a testament to the universe's breathtaking scale and intricate design. Every spiral's graceful turn, every galactic collision, every stream of stars stretched across the void whispers the same truth. The cosmos is alive with motion, shaped by forces both seen and unseen. From the invisible grip of dark matter to the explosive feedback of newborn stars, we've uncovered astonishing layers of this celestial choreography. Yet with each revelation comes a humbling realization: we're only beginning to decipher the universe's grand narrative. Think of how far we've come. Centuries ago, galaxies were static smudges in the night sky. Now we understand them as dynamic actors in an epic saga, where gravity scripts every interaction and dark energy stretches the stage itself. Tools like the James Webb Space Telescope and next-generation supercomputers peel back the veil further, revealing galactic winds that sculpt entire galaxies, magnetic fields that steer cosmic storms, and black holes that orchestrate stellar motion from the shadows. But the more we learn, the more mysteries emerge. Why do some dwarf galaxies orbit in improbable planes? What triggers the sudden awakening of dormant black holes? How will dark energy reshape the cosmic web in trillions of years? This endless curiosity is what makes astronomy so thrilling. Unlike a puzzle with a fixed solution, the universe keeps rewriting its own rules, surprising us at every turn. Take dark matter. We've mapped its influence across billions of light years, yet its true nature remains elusive. Or consider the Great Attractor, a gravitational anomaly pulling thousands of galaxies toward it, its full identity still hidden behind the Milky Way's dust. These aren't failures of science, they're invitations to dig deeper, to question and to wonder. What's next? The answer lies not just in more powerful telescopes, but in fresh perspectives. Citizen scientists combing through galaxy images have spotted anomalies professionals missed. Artists sonifying cosmic data have revealed patterns invisible to the eye. Even you, right now, might glance at a simulation or a star chart and notice something no one has before. That's the beauty of this journey. It belongs to everyone. So whether you're an avid stargazer or someone who's just discovered the magic of galactic collisions, remember, the cosmos isn't a distant stage. We're part of its story, woven into the same cosmic web that binds the whirl of Andromeda to the spin of the Milky Way. As we close this exploration, I'd love to hear what captivates you most about galactic motion. Is it the fate of our Milky Way, destined to merge with Andromeda, the eerie synchronicity of galaxies moving in unison, or perhaps the unanswered questions what lies beyond the Great Attractor, or what dark energy truly is? Drop your thoughts below, and if you've enjoyed this journey through the cosmos, consider subscribing for more deep dives into space's greatest mysteries. The universe has countless stories left to tell, and together we'll keep uncovering them one discovery at a time.